Thank you very much for inviting me to give this keynote lecture here today. It is about sheet forming and yield surface simulations where we consider microstructure, texture and damage by using our free software package DAMASK. And I will give a couple of introduction items and also show how we can apply it to sheet forming applications. I will highlight the contributions of all my colleagues who helped realize this project as we go along. We all appreciate that the metals market globally is huge, so we talk more than 3,000 billion euros turnover every year. And many of these metallic products are of course subjected to sheet forming applications, and that is the core of what we can do with our DAMASK package. Sheet forming properties are requested at the macroscopic scale, be it in forming simulations or crash simulations or related questions. The defects, however, that realize certain deformation or texture effects live at the atomic scale. That means we have designed our software over the past 25 years in a way that it reflects and captures the interplay between the defects, the macroscopic forming and mechanical properties, and the processing that leads to certain microstructure features. This is in our case very important since we think that a quantitative digital twin in manufacturing and sheet forming simulation requires to capture really the microstructural features of metallurgical products and processes. So mass and energy are of course conserved quantities, but a very important lecture to take home in our field is that microstructure and properties are not conserved, and they are also not in a global equilibrium but often only in a local thermodynamic and mechanical equilibrium. And that means that any digital twin, any simulation method of through process aspects or sheet forming simulation aspects require to be microstructure sensitive. This means the main philosophy of our software package is that properties are determined through the microstructures, and the microstructures are imprinted through the processes to which the material is exposed, and we need to describe these microstructures in a mechanism-based fashion. This is shown here exemplary for the field of aluminium alloys. This encompasses, of course, many different types of materials. And when we start with the so-called 1000 series aluminum alloys that you all know from packaging foils, which is relatively pure aluminum, as you can see here from this diagram. And then we go up the ladder towards the 3000 series alloys that you all know from can packaging, but also from architecture, and go further to those alloys that become really relevant for automotive and sheet forming applications, namely 5000 and 6000 series alloys, which are mainly blended by magnesium and silicon. And when we go to the high strength grades, then we see here the 2000 series alloys, and of course the ultra high strength 7000 series alloys that are typically blended with magnesium, zinc and copper. And of course these 7000 series alloys are also increasingly used in automotive forming operations. So what is really interesting in this diagram is that you have a certain influence by the composition. We have shown different alloying elements here, and you can see when just plotting the tensile strength, as in this diagram, how the tensile strength is affected by the alloy class and hence to some extent by the alloying content. However, from the huge bars you can also very nicely see the range that is influenced by microstructure and hence also by processing. That means within the same material class we have a huge variation of properties, both in terms of strength but also in anisotropy, surface quality, sheet forming properties, etc., that is affected by the microstructure. And this is another lesson and another fact that we use here to show that the simulation of such processes hence has to be microstructure sensitive. Let me give you an example of classical DP steel. This type of material, exemplary shown here, consisting of ferrite and martensite, is of course of very high interest in the field of automotive forming and application. It has a very high ultimate tensile strength, UTS, low yield strength, which is beneficial. It has a decent ductility of a few percent normally, good formability, no Lüders strain, tunable properties, and is very cost efficient. And when we want to increase the strength of these materials, you get this at relatively low cost, of course, but that means you require more martensite and a higher carbon concentration inside of the martensite, and this is reducing the ductility of the material. Now, when we zoom in for a moment into this material and take a look, for instance, at the martensite, then you see here an example where former austenite grain is reconstructed from the martensite. And these measurements have been done by electron backscattering diffraction. So that means from the crystallography you can reconstruct all these packets and lath interfaces as you see here. So the very fine structure that is so characteristic of martensite. And here in the electron channeling contrast image you can see the very fine substructure of the material, if you have to, even in 3 dimensions such as shown here. When you finally even resolve the microstructure in the transmission electron microscope, here edge on with all these fine features of the martensite lath lamella highlighted, and you overlay that even by an atomic scale measurement of the distribution of the carbon, then you also can see that the microstructure is not only incredibly complicated inside of the martensite, but also that the carbon is, other than typically assumed in martensite, not homogeneously distributed, but is decorating the lath interfaces. Now this is of course a very detailed view, and you could say, okay, why is that important for forming operations? And the reason is shown here. You have here a zoom in into such a martensitic nanostructure. You see here a coarse lath inside of the martensite, which is adjacent to a set of very fine lath that are produced later during the quenching. And when you expose that in situ to a tensile test, so a tensile test that is done inside of an electron microscope, you can see that such areas of high mechanical contrast initiate, for instance, damage during a forming operation. So this is just another area to which we later get back, namely to show that also if you want to predict the evolution of microcracks and damage during forming or during crash simulations, you need to consider the microstructure of the material. This is a very nice example from a collaboration effort that was funded by the German Science Foundation through the SFB 761 that was done in the Institut für Bildsame Formgebung by Markus Bambach and Gerhard Hirt at the University in Aachen. And it shows the comparison of a TWIP steel versus a DP steel. Now the TWIP steel, as you just saw before, has a very high integral below its stress-strain curve. And you would expect that it is a perfect material for such a crash box application. But surprisingly, you can appreciate here that the DP800 steel, with its much lower ductility compared to the TWIP steel, is actually performing much better in such a crash box application. So how do we have to understand that? The reason for this response becomes clear when you realize that in such a crash box application, only really the maximum loading points at these buckling areas are really loaded. And that means that you have only a very small area of the overall ductility shown here in the stress-strain diagram that you really use. That means the fact that the TWIP steel has such high elongation is not really exploited in such a type of application. So that brings us to the obvious and of course well-known fact that the energy absorption here depends on the material and of course on the design of the part. So again, we must really understand what kind of microstructure we have in the material. And on the other hand, such a digital twin must really reflect the tensorial microscopic response of that microstructure to be able to correctly predict the reaction of the material to such macroscopic boundary conditions. Now let us come to some aspects related to the simulation method. So we use the package DAMASK that we have developed over nearly 30 years now, and I'll show you an example how we applied an ICME, so Integration of Computational Materials Engineering approach, to the case of DP steel. First, we conduct a set of experiments to validate the program package. For that purpose, for instance, we can expose DP steel surfaces to silica patterns that give us a sufficient electron optical contrast. And then we can do tensile test experiments, as I've shown before, directly also inside of an electron microscope, or ex situ, do it in a tensile machine and then investigate it with these markers in an electron microscope subsequently. A very important trick is here that we use in-lens detectors in our electron microscopes so that we are free of the typical surface features that in DP steel and other high-strength materials are typically giving too much contrast for the picture to pick up the local deformations by digital image correlation. So with that trick of in-lens detector sensing in our electron microscopes, we can very nicely reveal the deformation patterns that are emerging when you deform such types of materials. And as I will show you later, we also can do that in 3 dimensions, because particularly in such finely structured materials like DP steels, this is quite important when you want to have simulations with high fidelity. And then we can extract the strain maps from that. Now, how does this communicate to the simulation strand? First of all, we have to take these microstructures that we detect prior to deformation and have to turn them into digital models. This can be done quite automatically due to the sufficient contrast for the 2 different phases that you get in the electron microscope. We have then different ways how we get the mechanical properties of both the ferrite and the martensite. This is done here still by indentation testing, but we can also meanwhile inversely obtain these data from macroscopic tests. And then we can put these data together with the corresponding microstructure maps into solvers such as finite element solvers or spectral solvers. And then we arrive at corresponding prediction of the stress and the strain map at a microstructure level. Let us go a little bit more into the kinematics and into the underlying kinetics of the deformation. So in such metallic materials such as steels and aluminum alloys, the plastic deformation is achieved through the motion of dislocations. Just to remind you of the enormous quantities of these dislocations, when you have a cubic meter of crystalline metallic material, then you have up to 1 light year of dislocation length into such a cubic box. That means about 10 to 16 meters per cubic meter. When you see such shear steps as here at the surface of such a nice single crystal test, just to reveal the mechanism, you see these steps correspond to the activity of many such dislocations as you see them here. And in that so-called Urovan equation, you can translate that here through the gamma dot, which is a local shear rate written in the coordinate system of the respective glide system. You can express that in terms of the mobile dislocation density, the Burgers vector, and the velocity distribution of this dislocation population. Of course, in reality, in real polycrystals that you use in sheet forming, you have of course also interfaces like shown here, like grain boundaries, that are natural obstacles and reduce the mean free path of those dislocations and thereby enhance the flow stress of the material. In modern steels, you of course have also mechanisms of athermal nature, such as the so-called trip and twip effects, where trip stands for transformation-induced plasticity and twip stands for twinning-induced plasticity. Here's an in situ electron microscopical movie where you see when in such a trip steel martensite is formed, you create not just the martensite and the additional interfaces, but you also create huge populations of dislocations that you can see nicely here because of the misfit that is created by the martensite. Here you see a TWIP effect, and in this twin you can see a spatial confinement. You can see in the electron microscope during loading how the dislocations have now to expand inside of such a twin, which also confines their bow out length, and this gives a hyperbolic relationship between the stress increase and the internal length scale. So the basic kinematics is shown here for the individual slip systems. So the slip systems are activated due to reaching a certain local critical shear stress. And this local critical shear stress has to be, of course, calculated by the external loading, which is then translated into the glide system of the material. And in body-centered cubic material, like for instance ferritic steels or some of the martensite types, which are either tetragonal or cubic, you can have up to 48 different slip systems. So when we plot this in a so-called single crystal yield surface, such as shown here, and we only cut a two-dimensional section out of this single crystal yield surface, then you can appreciate how these kinematic lines look like when you only plot the 110, 111 glide systems, where 111 half is the Burgers vector and 110 is the first type of glide planes in body-centered cubic ferritic material. And then you can do the same thing for the 112, 111 glide systems, which also occur in ferrite, and you get an additional family of glide planes, as you see here. And when you even add the 123 111 glide planes, then you have a relatively homogeneous plastic flow in terms of the kinematics in each single grain. So this is the orientation dependence of the kinematics that you have at each orientation point in your mesh. When you have all of these systems active, then this is even a relatively isotropic response in BCC ferrite, as you see here from the von Mises ellipse. Now, how are all these constitutive aspects now acting together in our DAMASK simulation package that is shown here? We have the elastic anisotropy covered because you also need to calculate things such as a springback effect. We have the phase fractions covered. We have the defect dynamics that I showed you before. And we have here a coupling between the local microscopic shear rates and these internal shear carriers that I've mentioned before. This is a kinematics that I've shown you just on the slide before, how we translate now this into the local orientation factor, which is a duadic matrix of the Burgers vectors and these plane normals, also often referred to as Schmidt matrix. And then of course you need the orientation information that can be measured locally or in 2 dimensions, 3 dimensions, or just globally by XRD or synchrotron diffraction. These are standard techniques today. Then you can also, because you may have too many crystals to consider, you can of course also choose different types of homogenization schemes where you average the local response of the crystals acting on one integration point like shown here. And as I show you at the end, we can also consider damage models in the material. Here are just some rather old experiments where you see a pure aluminum columnar microstructure with very big grains. So this is an experiment which has been taken by EBSD, and the color code comes from the digital image correlation. So these are experimental data that have been taken from a so-called channel die experiment. That is shown here in a little simulation sketch. That means you put your samples into such a channel die under good lubrication and take it out after a deformation step in order to measure the surface deformation in terms of DIC and the texture changes. This was done like about 20 years ago to get a feeling about the validation of these types of computer codes. So these are all the experiments, and you very nicely see the enormous heterogeneity of the deformation as shown here in terms of the local accumulated von Mises strain. When I deform the entire polycrystal here to even 15% in such a channel die setup, you can see that some grains are very highly distorted, as you see here, while others, like this rotated Gauss grain in the center, remains practically undeformed, just because of the different crystallographic orientations. And this is now a 20-year-old finer element calculations when we started to put this into these constitutive laws that I've shown you just a minute before. And we have done that also for three-dimensional objects, where we really in a painstaking and detailed way went through a validation of the software by such types of experiments. And also here we found very good agreement between the simulations and the experiments. And let me now show some more specific and more recent applications of the DAMASK software. Let us first talk about DP steel again, with which I also started off. Here you see an EBSD map, again consisting of the coarse ferrite grains and the fine martensitic islands in between. Now, when you subject such a microstructure to a DAMASK simulation, micromechanical simulation, as I've shown you before, you see already a wide range of micromechanical response. First of all, of course, you see up to 1 gigapascal tensile response, as you see here in terms of these blue areas. Surprisingly, however, you can also see some compressive regions, which are simply due to the fact that you have adjacent regions which are forming closer together, so that they put the material between them under a compressive load. And when you compare now in detail these experiments, here from the electron microscope, from the image quality and the DIC, and the simulations that I've just shown you before, in terms of the fine details, you see a couple of features that are quite nicely reproduced. So the global deformation of martensite versus ferrite is captured quite nicely, but the higher concentrated deformation peaks, which are highlighted here in terms of the red color, are often not captured very well in high fidelity between the experiment and the simulation. So that prediction was not very good. And the reason is that the world is, of course, in the microstructure scale also three-dimensional and not just two-dimensional. I show you here an example where we probe such microstructures in full 3 dimensions. This is an apparatus that has been developed in my colleagues group from Stefan Zefferer over many years, which allows you to conduct completely automated 3-dimensional serial sectioning of such complex microstructures. You see that such a sample, after having been polished in this automat, is put fully automatically by the robot into an adjacent electron microscope. So it's placed inside of the microscope, and in this instrument you can then measure the microstructure, the texture, the grain shape, all the things that you want to know. You can see how the robot is entirely autonomously closing the microscope and starting the corresponding measurements. And then it's taking afterwards the sample out again and does it all over again. And that creates such data sets as you see it, fully 3-dimensional, with all the faces, twins, orientations, and all the information that you might need for subsequent simulation and homogenization. So that is here again such an example taken on a DP steel. And when we put this now in a 3-dimensional form, due to the very fine martensitic islands, into a corresponding solver, we get the stress and the strain distribution also in full 3D. Again, these are of course relatively small chunks of material, but we need to know such validation testing in order to use these approaches as homogenization tools for large-scale, for instance, sheet forming operations. Now here you see such a 3-dimensional data set taken in the way that I've just shown you before. And here is a corresponding digital map that we created from it, of course, plus the corresponding orientations of the ferrite, but also with a full appreciation of the positions of the martensite. And now this is done subjected to a corresponding FFT spectral solver calculation with the DAMASK software, and you get a much higher fidelity simulation of the corresponding equivalent strain and equivalent stress. So that means for some of these really complex steel microstructures, it is quite relevant when you develop new homogenization tools that you are able to reflect certain three-dimensional features of the microstructures properly. Now let me show some recent examples from sheet forming simulations conducted with our DAMASK software package. Here we conduct a classical coupled mark simulation in a standard finite element solver, in a commercial solver, where we use one of our homogenization methods. So that means each integration point is representing such a chunk of material that I shown you before with an underlying homogenization method. So these homogenization methods can be picked from the DAMASK solution, and they can be isostress, isostrain, or more complex Taylor type of models or self-consistent type of models that are behind the local representation of the stress feedback at each of these integration points, representing the local microstructure behavior. Another approach is the direct mapping of the microstructure in yield surface simulations. So here the idea is to approximate the coefficients, for instance, of yield surface functions by such microstructure crystal plasticity simulations, or you can also on the fly permanently update and iterate the corresponding yield surface functions depending on the rate of change of texture and stress feedback, which you then read out in a corresponding microscopic sheet forming or cup drawing operation simulations such as shown here. So these are the classical functions. We use different type of yield functions. I later get back to these. You are all familiar with these features of these yield functions. And we use a simple isotropic hardening model. Of course, you can use different type of hardening models. And we retrieve then locally to the crystal plasticity kinematics that I've highlighted to you before. So I don't repeat here going into these individual details. And the idea is that we now fully couple this through a Python routine between DAMASK and the corresponding macroscopic simulations. Now here are some of the results. We have here picked two different yield functions that you see here, the 2004 18P and the 2002D, fitted either to experimental or to crystal plasticity data. What is important here to realize, both for the normalized yield stress and also for the R values, for the Langford values, that we considered here only the central layer texture of the sheet. And you see that you get a deviation between these two approximations. When you now, however, use a complete texture, which, as you remember, in some of the materials, sheet materials, can be different between the surface and the center, you get a much better agreement between the two. Now these are the corresponding yield surfaces. Here we show first both yield surfaces, the 2002D and the 2004 18P, fitted to experimental data. And of course as they evolve with the deformation. And here you see it now again fitted, but only to the central layer texture by using crystal plasticity calculations. And this is a corresponding comparison where we use the complete texture integrated over both the center and the surface of the material. And these are the type of simulations that you can then obtain. This picture shows the deformed configuration and the equivalent plastic strain shown in terms of color code, simulated now with the yield 2002D. And this again considered only the central layer texture, just to show you the difference, what kind of microstructure feature you are considering. And here are also the final textures shown at three different important positions in the material after the cup drawing simulation. Now this is the same type of diagram, but now we did the simulation by again considering the complete crystallographic texture through all the main layers. That means mainly the surface and the center sheet layer. And here you see the same for another yield function for the 2004 18P, first starting with the central layer texture, and we did the same of course also for the full texture. Here's another example beyond the classical sheet forming that we can do the same, of course, for more complex operations or beam bending operations here with the DP steel. We then also again can zoom in and analyze the local micromechanical response from the underlying RVE. RVE standing for representative volume elements. This can be very important, for instance, when you want to better understand where failure or strain localization or stress localization in the material is formed. This is very important to better understand the micro damage that is evolving inside materials. So this is just a little bit of a projection of some very recent work. When we stay for a moment again in the world of the dual phase steels, then we have compiled here in this overview paper the martensitic volume fraction plotted against the ferrite grain size and compiled then the corresponding damage mechanism in these different areas, which can be either martensite cracking, which then leads to a fracture that is carried into the ferrite material, or martensite ferrite decohesion, as shown in this picture. And in this region you can get both depending on your underlying microstructure. So this is kind of a classification scheme that gives you a rough direction how your material will respond. And this can be really quantified over big chunks of material. And this is something that we can correspondingly reflect nowadays by the predicted hotspots, micromechanical hotspots at the regions of high mechanical contrast in such DAMASK simulations. We have also modified the software in the direction to consider a corresponding variation of the Allen-Kahn theory that is capable of simulating the gradual evolution of damage out of the microstructure. That is shown here in 2D and 3D sections, where you see how damage is evolving here out of the martensite fracture, then evolving and growing inside of the ferrite material, as you see here, until it starts really percolating through the material. And this is a 3D view of such results. So that means we are now capable in DAMASK to predict the local evolution of microstructurally initiated damage in complex engineering materials. Another very recent application is the connection between crystal plasticity, through dislocations mainly, and phase transformation. This is very important when it comes to the simulation of complex aluminium alloys, because in aluminium alloys, you remember, you have complex coarsening phenomena of the microstructure when you, for instance, expose the sheet to higher temperatures and you want to know how such morphological changes in the microstructure translate to hydrostatic stresses and to the formation of plastic strain. And that is done in a recent implementation in DAMASK, where we combine plasticity, phase transformation, diffusion, and Oswald ripening. This is realized in the underlying models by combining crystal plasticity with phase field and with Allen-Kahn type of simulations. So one last word about microtexture modeling. When you, for instance, want to do sheet forming simulations at very small dimensions, or want to better understand the evolution of microstructure and microtexture inside of grains, we are currently working on a variety of different mesh refinement methods. That is shown exemplarily here. We start again from a representative grain microstructure, such as shown in terms here of the color codes, but with 3 different grain sizes, mesh sizes. And when we subject these different simulation boxes to a thickness reduction of about 50%, then you see that already in the highly refined grid, you see much finer details, of course, inside of the individual crystals emerging than compared, of course, to the coarse grid. And when you push that even a bit further to 75%, then you can see that when comparing the coarse grid simulation to the fine grid simulation and to the highly refined grid simulations, where we can refine the mesh on the fly, you see that you have a very highly resolved simulation that is meanwhile very hard to differentiate from an experiment. When we zoom in for a moment, you can really see these fascinating details out of a pure simulation emerging. So these are of course very fine details that you would typically not need in a sheet forming operation, but they can be very relevant, for instance, when you want to predict things like recovery, recrystallization, damage evolution, small scale deformation effects and related phenomena. And when we summarize some of these features, you are referred to the webpage of the DAMASK software package. Please remember it's entirely free and free of any costs. And we are happy to collaborate and talk to you about detailed application questions that you might have. And we have meanwhile many customers in university, in academia, and in the industry. And this is just a small snapshot. Meanwhile, we again have many more customers who make use of our software. And you are also welcome to contact these companies regarding their experience. And in a little summary, let me remind you of the fact that this package contains damage evolution theory, phase transformation theory, and also sheet forming theory. So that you have a complete package that ranges from the microstructures towards implementation into large-scale forming operations. And with that, I would like to thank you very much for your kind attention, and I would be happy to take questions. Thank you very much.